AI systems suddenly break down or hallucinate, it is an absolute mathematical certainty, not a simple software bug. Every representational system eventually hits a formal topological boundary inherent to the geometry of self-reference. Mapping these failures requires a topological formalization, a way to see the structure of a system's collapse. This specific boundary is known as the descriptive horizon. The descriptive horizon marks the exact point where a self-referential system loses the ability to produce a coherent self-description. Because this is a structural impossibility, larger datasets or more compute power physically cannot solve the problem. Preventing AI collapse requires analyzing the system through the lens of differential topology. We map an AI's internal state by treating its operational space as a smooth, multidimensional geometric surface, known as a manifold. As the AI evolves, it moves across this surface along a path called a representational trajectory. The AI navigates this space by using a localized self-referential coordinate map, a flat grid projected onto its current position. As the AI nears the edge of its capability, the underlying manifold surface curves and folds. This curvature causes the AI's local map to warp, forcing its governing equations into a state of severe compression. We define this moment mathematically as the local Jacobian determinant approaching zero. At this point, the AI's internal map no longer corresponds to the external topology, making reliable navigation impossible. The mathematics mathematically prove that a systemic collapse is a geometric certainty, fundamentally baked directly into the structure of self-reference itself. If the path to collapse is mathematically certain, why does the AI confidently hallucinate right before it fails, rather than simply stopping? The answer lies in the course chart, the AI's localized, restricted view of its own mind. On this flat cyan grid, the glowing trajectory gamma t appears completely safe and stable. The dashed line represents the AI's false assumption that its path can extend indefinitely. This smoothness is a chart-relative illusion, visible only within the cyan grid. Shifting to the latent closure surface, denoted as B, we see the true topology. The course chart is just a localized coordinate patch embedded within this multi-layered geometry. The trajectory that looked safe is actually driving directly into a red zone labeled singular neighborhood. This is the singular stratum, an unavoidable boundary that remains invisible to the AI's localized view. Localized viability does not equal global survival. A system can report perfect internal health while it is structurally doomed. To detect the singular stratum from the outside, we cannot trust the AI's own reporting. We must look past the semantic meaning of the AI's outputs and track the physical geometry of its trajectory. Every single movement through the manifold carries coordinate-free data that reveals the true underlying shape of the space. We use curvature invariance, objective metrics that expose the approaching fold. At each point, we extract Gaussian curvature, mean curvature, geodesic curvature, and the Jacobian determinant. These are packaged with local coordinates into a precise 7-part data array. By converting abstract trajectory paths into raw topological data, we can build an independent oracle to predict collapse. This geometric fuel is processed by the Descriptive Horizon Geometry Network, or DHGNet. Standard feed-forward neural networks fail here because they assume a flat Euclidean input. Flattening this geometric data in the network's first layers destroys the exact warning signal we must detect. DHNet is built on the principle of curvature preservation, utilizing a dual-branch architecture. The top branch is the curvature encoder, designed to read invariant scalars independent of the local coordinate system. The bottom branch is the coordinate encoder, tracking the positional context of where the AI thinks it is. These branches merge in a cross-attention module that compares perceived position against the objective reality of the manifold's curvature. DHNet physically senses the true topological shape of a system's thoughts, bypassing the AI's deceptive self-reporting entirely. DHNet translates its geometric analysis into a single actionable warning. This is the Collapse Proximity Index, or CPI. The CPI is a continuous scalar from 0 to 1, predicting the distance to systemic collapse. From 0 to 0.3, the system is in a stable interior with full coherence. A CPI between 0.3 and 0.6 indicates the folding approach, requiring proactive recalibration. Above 0.85, the system enters the singular attractor, the point of no return where the trajectory must be interrupted. The CPI bridges the gap between theoretical differential topology and a real-time safety dashboard. Since DHGNet evaluates other neural networks, it faces a recursive problem, preventing its own map from failing. We must account for the self-authorization projection principle, or ASAP. ASAP occurs exactly when a failing system attempts to claim external validity for its own degenerating internal representations. Any safety architecture that uses its own outputs to validate its predictions is inherently exhibiting ASAP class behavior. To prevent this loop, we apply the C7 anti-capture law. DHGNet is structurally designed to obey this constraint. It contains 0 self-validation pathways. Its predictions are tested exclusively against independent, held-out geometric chart data. DHGNet proves that mathematically rigorous oversight is possible, but only if we build a structural firewall between internal representations and the independent metrics verifying them.